Hi, everyone. Welcome to PyData Global. We're excited to have you join us. Please feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you do have any questions, please post them in the Q&A tab, and we'll address them at the end of the session. But now it's my pleasure to introduce Jeff Bezanson. He will be presenting his talk, Statically Compiled Julia for Library Development. Jeff is a co-creator of the Julia language and a co-founder of Julia Hub, and we're very excited to have him presenting today. So thank you very much, and let's give a warm welcome to Jeff.
All right, thanks very much. Can you hear me okay?
Yep, sounds good.
Okay, great. All right, thanks for joining, everyone. So I'm going to talk about using Julia for library development today, or somewhat teasingly, can Julia replace C++ in some cases? If you've heard about Julia, it's no secret that we were kind of after the MATLAB, R, and Python programmers. We wanted to make a convenient, easy to use, interactive front-end language that you could use for interactive computing, data analysis, plotting, but that would also run fast. So that was our initial sort of target use case. But as we developed and we found that actually we got sort of an equal amount of interest from C++ and C programmers who liked the speed. So it turns out, there was more to it than that. And we talk a lot about, what we call this two-language problem, where you're forced to develop a system in two languages with a front-end language and a back-end language for scripting, for convenience, and the C on the back end for performance. And if you don't, if you can avoid that, I think you should avoid it. And Julia is designed to address that. But you can't always avoid it. And sometimes you don't want to avoid it. There are lots of cases where you have Python programmers who are happy to call libraries through Python interface. And in some cases, it works very well. They like it. It's productive. And you might as well just keep doing it. There's not always a reason to change that situation. And so especially if you have a library that's has a very large number of Python users, they probably don't want to all change what language they use. But there might be a much smaller number of people who develop the library, and those developers might want to change the language they use to get to more productivity on the library development side. And that's probably much easier because only the small number of developers of that library have to change languages, and all of the end users do not have to change languages. So this is a really good use case for Julia, actually, to replace the performance part of development, not necessarily the front end part. And this exists already. So there are already Python libraries that are written in Julia. So for example, you can call the Julia differential equation solver stack from Python. There's a package for that. diffeqpy, which you can find here. And similarly, there's bindings for R, diffeqr. You can find it in CRAN. So people have already made bindings to call certain Julia libraries from Python. They use this incredible package called Julia call. Unsurprisingly, on the Julia side, it's called Python call, but it's basically a bidirectional interop package that's really quite amazing. It lets you do basically everything. You can use everything in Python in Julia and everything in Julia from Python quite easily. Pretty much everything works. It's really impressive, and through that you can just call any Julia library from Python. So it's all kind of available already. So all right, so you can develop Python libraries in Julia. So that's already done, right? Already set. Well, maybe not quite. And the problem that you're going to run into is basically the footprint of the thing. So when you install, say, diffeqpy, what actually happens behind the scenes is it's going to install a full Julia environment. It will then download and precompile all of the required Julia packages, which can be quite a large amount of code. And then so when you do that, the first time you use it, you're tapping your fingers for several minutes. And I think the whole size of the thing that it's going to take up on disk is, I think it's around a gigabyte, because it's just a lot of code. And the reason is basically just that's giving you full flexibility. So if you really wanted to you could actually immediately start developing those packages. You could modify them and try it out. You can use everything that's in there. You have kind of full flexibility. So it has kind of a, maybe an excessive amount of degrees of freedom, because it just gives you everything. But that's not always what you want. This is not so great for smaller system, maybe HPC systems, something like that, where this might not be a good user experience. So we are now addressing this and trying to create a build and deployment workflow that's much more similar to what you would do in C and C++, that doesn't require kind of all of this heavyweight installing of all of these environments and everything. So we're working on that now. So we're adding this feature called trimming, which is going to be in Julia 1.12, and it's basically just this -- trim option, along with a new compiler driver script to make it easier to compile things. And that basically will just remove absolutely everything that you don't need for a particular specified library interface. So I'll show a little bit of a demo of what that would look like. So for example, I could write libm, the standard C math library in Julia, and I could do it like this, for example. So I've got a module, my libm, and then I just write out my functions. So I've got, I put @ccallable on here, which this is basically the equivalent of extern C in C++. So that's going to create a C ABI compatible and non-mangled named sign function in the output binary. And in this case, I'm going to implement it just by calling the Julia base sign function. And you see, I've got two signatures here. Since it has to have a C ABI, I have to specify the argument types and the return type. But then, of course, the sign function is a generic function, so it handles any arguments. So the implementation can be the same. And this is actually, this is not cheating as much as it looks like, using sign to implement sign, because in Julia, this sign function is actually implemented in Julia. So we don't call the standard libm sign function anymore. We've gradually replaced basically all of these standard math library functions with our own implementations in Julia. So this is actually a proper fully Julia implemented libm, albeit only with the sign function, but this is a good enough demo. So I've got that source file, and now this is the steps I would do. So I run this juliac.jl script, which is in the contrib directory of a Julia source tree. And I say I want trimming, so I put -- trim, and I can say -- compile ccallable. And what that basically means is it says anything that I've marked @ccallable, I want to be considered an entry point. So I want all of those to be available. So that will include all the ccallable things. If you want to include things that are not ccallable, there's a function you can call to declare entry points, and then that's how you would do that. But for CABI, that's the easy way to do it. And say I want to output a library. Let's call it my libm and the source file, and that's it. So I run that. It takes about 30 seconds, and then I get this out. So I will simply get a .so. So as of now, it's about 1.7 megabytes, which is not all that small. It's not tiny, but it's pretty good, because here we're comparing against this very heavyweight, multi-hundred megabyte, I think even gigabyte install footprint. So it's actually a massive reduction. And so in this, actually this is it's actually half debug symbols. So if you run the Unix strip command on this, it already goes down to about 900K. So it's pretty reasonable, and we're still working on it. So there will be further reductions to the size of this in the future. So we're still working on it, and this also does still depend on the Julia runtime. So there's a libjulia that would have to be installed that this links to, but that's actually not that big. The libjulia is only a couple megabytes. So the whole thing is just a handful of megabytes. So it's actually a huge reduction, and it's getting better, but it's already pretty good. And then you see I can start up Python, load C types, and just load this as a DLL, and I can just call the sign function that's in there. All right, so when you use this, it opts you into a few limitations because we can't, in general, know all the code that's reached since Julia is dynamically typed. And of course, some things will break if you do things like reflection. Well, some things have been removed, so you're not going to necessarily get the same results from stuff like that. And we add some compile time errors to facilitate this. So if you have basically things in your program that are too dynamic that we can't figure out what's going on, it's going to be disallowed. And there's a few common problems, like of course things like generating code at runtime, like eval, or looking up global variables by names. The standard out variable is dynamic because you can redirect the output stream at any time. So if you use our std out variable, we don't know the type of it because it can change at any time. So there's a few common problems that you might hit if you try to do this, and you'll see something like this. So when you do that Julia C with trimming, you might see some output like this where it will say, okay, there's a dynamic call here that I can't resolve. I don't know where this goes, and it will show you the location of that error. So we're kind of getting into the world here of more, more of a statically compiled sort of workflow. And so for the maybe C++ library developers out there are some reasons why C++ programmers might like Julia. So it turns out there's actually a pretty good mapping of features between the languages. So if you like the features of C++, you'll find that the similar things actually exist in Julia. You have basically things that are like templates. You get specialization and speed. There's good C interop. And we have lots of kind of drill down. Like you can see the generated code and assembly code very easily. You can do things like manual vector instructions, write GPU kernels by hand if you want to. You can use pointers directly if you want to. So you can get down to those really low levels if you really want to. So, all right. So for example, just to see some feature mappings. All right. So overloading, Julia uses multiple dispatch generic functions. So that's really straightforward. Clear that you can do that same kind of multiple, signatures per function as in C++. And methods, since these are dynamically dispatched, it's basically the same thing. You just, we dispatch by the argument types. So we don't need a separate feature for that. So you have the equivalent of methods as well. And templates, they have this kind of where syntax. So where you have a template with a type name in C++, you just do this where t, and it's basically the same thing where you're declaring effectively a pattern of method signatures. And template specialization as well. So if you have that general template function, but then you want to also specialize for a particular case, you can do that as well in Julia. So all those kinds of powerful features for specialized and composable programming are there. And one thing we've been working on especially recently is static analysis. So there's several static analysis tools for Julia, and they're actively being developed. So one, for example, is semgrep, which is sort of used typically for like security auditing kinds of things, or finding potential problems in your code. And so they've last year they added support for Julia, and we have an interface to this in Julia Hub where you can basically click on a package and we'll show you a list of the errors that are possible problems that are found in it. We have another interesting tool called AllecCheck, which you can use if you would like to avoid dynamic memory allocation in something. So if you're doing like a control loop where you don't want to have any GC pauses and you want to be sure that it doesn't allocate any memory at runtime, you can just do this check Alex, and it will tell you where any possible allocations are. And if it's empty, it means there can't be any. So if you really need that kind of thing, that tool exists now. And so really the vision of all of this is, you write your code however you want, and then you kind of put in your requirements. I want I want this to be this type here. I want this not to allocate memory. I want the smallest binary possible. Put in all your requirements, and then everything gets sort of checked, and there's tooling to help you sort of achieve that goal. So that's sort of the goal here. If you like more compiler errors, we have this tool Jet, which you can run it on something. So here I ran it on the Julia standard REPL, which the REPL is, it does some sketchy stuff. So I figured there'd be some possible issues in there. And indeed, yeah, it found a few interesting things, like possible accesses to undefined variables. I think those are maybe false positives, I think, but you can get compile time errors like this, possible matching method, and so on and so on. So these kinds of static analysis tools are coming online, and if you like that kind of statically compiled, statically typed workflow, that's going to increasingly be kind of optionally available in the Julia world. So yeah, Julia can replace MATLAB, okay, maybe. And it can build binaries, and it has static analyzers. Maybe it can replace C++ sometimes. All right, that's it. I will take some questions. Let's see.
Hi, Jeff. I think we have two questions.
Okay.
So the first one is from Daniel Final, and he's asking, about the two-language problem. I think Peter Wong just gave a keynote address about 30 minutes ago, or maybe an hour ago, and he's wondering if the two-language problem maybe wasn't that big after all, and how does this fit into the two-language problem?
Well, I think it's entirely application dependent. I mean, it's in some cases it definitely was a problem. Yeah, but it really depends on the application. So yeah, as I said, there are cases where the assumptions that makes actually do hold. Like if all of the time is in the libraries, and you don't really need to extend or develop them very much, and you happen to like using it from the scripting language interface you're using, then yes, maybe it works. So I think if certain assumptions hold, then yeah, maybe it's fine. But in other cases, it really is a big problem, and a lot of those users are moving to Julia. But it's not 100% of cases, clearly. So it's really application dependent.
Cool. Actually, I think Daniel has a follow-up question. See if we can get him onto stage. He's also asking about, do you think this can really replace C or C++? Do we still need C or like a static language like that to continue to be a backend? Or do you think we basically should replace it because maybe Julia is more memory safe?
Yeah, well, if you want just safety, of course, yeah, Julia is memory safe. But of course, there are other options too, like Rust. And of course, some people are migrating from C++ to Rust. So it'll depend on your tastes and requirements. And yeah, so I mean, of course, some people are very happy with C++. They have big, legacy code bases. They don't want to rewrite it. In that case, that's fine. But there are some people for whom C++ is a hindrance, and they would rather use a higher level language, but they just need the performance. And so that's where we come in.
Are these statically compilable Julia libraries relocatable? Can they call into Rust or C or C++ libraries via C call in the same way that dynamic code can?
Yeah, you can use CCall. You can use all of the normal features. Yeah, absolutely. Everything like that still works. So yeah, these libraries can also call other C libraries, of course. Yeah.
Well, I still think there might be a relocatable issue because, but I think we might be able to handle that on the Julia side. Although
yes, well, they really the only real dependency for it. Well, it depends. If you're using lots of libraries, if you have lots of dependencies, it might be a bit harder. But just for something like a simple case like I showed, it only depends on libjulia. So as long as it can find libjulia, it should be fine.
Okay. And I think, as long as we deal with the LD library path issues and other kind of dynamic library loading.
Yeah, it's
That
just
should
this,
work.
just the standard library locating and linking issues is the only real issue.
Great. I think this is a long-awaited feature in this. Now, currently, I noticed that this is a script in the Julia Git repository. What's the best way for people to use this feature right now?
So if you want to use it right now, I would get Julia Master because there isn't a released version that has it yet, but there will be pretty soon. But yeah, so you get clone the main branch from Julia GitHub, and you'll find it there in contrib.
Will this be part of the standard Julia release, or this is going to be like a separate package that you could add on?
It'll be in a standard Julia release.
Got it. Okay, so I hope I answered Daniel. You've answered Final's question. Daniel, if you still have other questions, please follow up. Kind of my question is, I'm coming from outside Julia ecosystem, looking at this. I'm also comparing the solutions like Cython or Nextcode and the MATLAB compiler and the MATLAB side and solutions like this. What do you think differentiates this capability for Julia from those kind of solutions?
Yeah, well, those of course are all related. Everyone wants to build binaries, so yeah, those kinds of tools also exist, of course. I mean, the main differentiator is the Julia language. A lot of people just really like it because it is very concise, powerful, composable. It's really just for the benefits of the Julia language with the benefits of a small binary. That's what it is.
I see. So do you think that, as a designer of the Julia language, was this always a goal that you had? And do you think that incorporating this into your initial conception of Julia helps now in this situation?
Yeah, it kind of was. I mean, what I wanted was to basically decouple what you can do with a program from the language itself. So, the languages tend to be these kinds of big bundles where everything comes together. Like you get this syntax, this type system, this compilation model. You sort of opt into all of those at once. But I think they should be more decoupled. Maybe I like the Julia syntax, but okay, today I don't care about small binaries, but oh, now a case came up where I need a small binary. I shouldn't have to switch languages just to a language that has smaller binaries to get that. I should be able to get that from the same language. So I really do want to decouple all of these things where you can kind of separately opt into the requirements and restrictions that are useful to you.
Yeah, I think this has very strong potential to make it easier to distribute Julia code in certain cases, where people don't necessarily want the Julia front end, but definitely want to use Julia in the back end, as you mentioned. So how do you see distribution getting easier now? And so are we going to say have like a minimal Julia install that's just libjulia that could be easily incorporated into a Python or say Conda package?
Yeah, I think though there will probably be a kind of a runtime only Julia distribution that just has the minimal runtime.
How do you think that Julia code base is changing? I noticed that we've been maybe taking some things out of the standard library. Is that an attempt to minimize the Julia footprint to basically only get what you need from Julia and nothing more?
Oh, you mean yeah, the refactoring of the standard library and kind of moving things around. That's more for development convenience that we are gradually moving things out into separate packages and separate repositories, just because it's just too much to handle in one repository. That's really the motivation for most of that.
How does this interact with ahead of time or pre-compilation for individual Julia packages? Can we use those binaries together with the static compilation so we have a semi-modular system?
Well, so this is kind of a much stronger version of pre-compiling. So in this, everything you'll need is going to be exhaustively compiled. So whereas the the existing package precompile stuff is designed for the case where you're using it interactively, so we don't know what the user is going to request. So we're sort of guessing and pre-compiling like a range of things that are probably useful. Whereas in this, you're compiling exactly everything that's going to be needed at runtime based on what the entry points are. So it's kind of a stronger version of that.
I see. So this is clearly distinct from kind of the system image approach, where we
Yeah, it's pretty different. Yeah, because it's about compiling exactly what's needed instead of sort of compiling as much as possible in the hopes that we've compiled what you're going to need when when you type something at the prompt.
Do you think there's any friction between having kind of these two different tracks for ahead of time compilation between the system image kind of Julia building versus this kind of approach? I think this to me, it sounds like this is more redistributable than a system image, which is rather specific to a machine.
Yeah, I mean, this is there is a little bit because of course you have to opt into these extra checks. So it's really only for the case where you really need the smaller binary. If you're just on a standard laptop or desktop, there's not that much wrong with the current way of doing things. So just install the Julia runtime in packages and just call them. That's perfectly fine in many cases. So it's really only if you happen to be in a case where the size is actually a limitation.
Does this now eliminate all compilation latency issues, or is that still kind of an issue?
Well, if you're running a trim binary, then there is no runtime compilation, so there won't be any compilation latency. Yeah, there's no, in this case there's no JIT, there's no runtime compilation at all.
Yeah, so it sounds like you solved a lot of problems with people using Julia ecosystem. What do you think is the next highest priority for you?
I think we have some more work to do on this, and then I would like to develop a fuller separate compilation model, because one of the problems with this is you can kind of you can kind of hack around it, but you can sort of only load one of these because we can only have kind of one instance of the Julia runtime. So we have a possibility of adding a real separate compilation model where you can load multiple of these and they can share a single Julia runtime, even though they're isolated from each other. And that's kind of the next feature. As it is now, each one of these would kind of have to have their own separate Julia runtime, which is kind of a technicality. But it would be nice for different binaries to share one, just to be even more efficient. And I think we'll get there eventually next.
Can you help me understand that? So is that a memory efficiency thing, or is it more like a multi-processing or multi-threading kind of issue?
It's so threading is one case, because you want a common thread runtime for all of your Julia threads. Yes, that's one good example of it. And another is just interaction. So it's actually if you have multiple compiled Julia binaries like this, it's actually pretty difficult for them to call between each other. They can call each other using ccall actually, but if they want to pass Julia objects, it's actually pretty difficult to do that because they're sort of isolated from each other and they might not know about each other's objects. It doesn't really work. So you can basically just use ccall between them, but you should be able to use a more like Julia native ABI to call between separately compiled binaries. So that's something that needs to be developed, but it's kind of technical. It doesn't stop you from just shipping a binary today, but it's something that would be nice to have.
Great. I think you've talked about this in another talk. Is how do you think this would help with deploying Julia to the web? Does this allow us to build static WASM binaries and push into the web?
We did have a WASM backend under development. There is one out there, but I think it's not very actively developed. So WASM is kind of a separate topic. But this does let you build executables as well. So I guess there are things that can run basically native executables in that environment. So this would make it. I guess it would just make it easier because there's a lot less code for it to translate. So. It'll probably just it'll probably just generally work better because you have such a much smaller binary.
if I recall, part of the issue was lack of a GC backend and WASM. Is that solved with this, or because we're kind of can bring our own GC now?
Well, I guess you can just sort of run the native Julia runtime, but yeah, no, I'm not an expert on WASM, but yeah, there is not I think there's not really a great usable native WASM backend today, but there is a project out there to do that. So it's been kind of demoed.
Okay, well, we got to close this session to go to the next talk. So thank you for that. Thank you, Jen, Jeff. This was a great session.
All right, thanks a lot.